In this lesson, we're going to talk about a theorem called the mean value theorem. And this is a very important theorem in calculus. But before we go on to talk about the mean value theorem, we're first going to talk about Rolle's theorem, which will help us develop the concept for the mean value theorem. So Rolle's theorem says, let f be a continuous function. So remember what we mean by continuous. So f is going to have like no breaks or holes or asymptotes or anything like that on a closed interval from a to b. So on two x values, so from x value a to x value b, on that interval, the function needs to be continuous. And then on the open interval from a to b, it needs to be differentiable. And remember, differentiable means that you're not going to have any points or cusps on that interval from a to b. And then the last criteria is that if you have your endpoints and you plug them in to the function and you get the same value of y, so f of a is equal to f of b, then there must exist a value of c, so another x value on that interval between a and b, so that when I plug in that value of c into the derivative, I'm going to get a value of 0. That is a lot of words, and sometimes it's hard to picture what that means. So let's go through the concept of that. If we look at the graph of A, we have an interval from A to B. So here's our interval from A to B. On that interval, it's continuous and differentiable, right? I don't have any asymptotes or holes or jumps or points or cusps or anything weird going on. And if you notice, if I plug in a into the function f, I get the same value for f of b, right? These values here are the same. So that's what this means here. So we already met the criteria that is continuous and differentiable over that interval AB. Now we've also shown that if I plug in the two endpoints, I'm going to get the same y value. So that means that there's got to be a value of c somewhere on that interval between a and b where the tangent line has a slope of 0. Meaning if I plug in that value of c on the derivative, I'm going to get 0. And the reason that is, if you don't have any breaks or holes or anything goofy going on, and if my y values are the same, if I come up, I have to come back down again to have the same y value, which means there's going to be some local min or max where the derivative is 0. Example A is an example of where you have a local max. Same thing on example B. I have an interval from A to B. That interval from A to B, the function is continuous differentiable. I don't have any holes or breaks or asymptotes or any points or cusps. So it's continuous and differentiable on A to B. And if you look, my endpoints at A and B have the same y value. F of A is equal to F of B. So that means at some point between there, I'm going to have a value of c where the slope of the tangent line is 0. So that's this point right here. So this is an example of where I have a local min. So in graph C, we have an example of where we have more than one value of c that gives us a derivative that is 0. This theorem guarantees there's at least one, but that doesn't mean there isn't more than one. So here's our interval A to B. If you notice, my two endpoints have the same y value. That function on the interval from A to B is continuous and differentiable. So then there must be at least one value, but in this case there's two values where the derivative is 0. So that's this point here and this point here. So we have a local max and min. This is our local max, and this is our local min. So that's the idea of Rolle's theorem. But you have to make sure, in order for this theorem to work, you have to meet all the criteria. It has to be continuous, it has to be differentiable on the interval AB, and the f of A has to be equal to f of B. So in this example here, this is where Rolle's theorem does not work, because the idea that from A to B, every point on that interval between A and B has to be continuous and differentiable. So if you notice in this example, the entire interval from -1 to 1 is continuous. However, it's not differentiable at the point x equals 0. So if I look on this interval, my value at x equals 0 is not going to be 0 for the derivative because it's not differentiable at that point. So here's an example of where Rolle's theorem does not work. All right, let's go through example A and example B here. We're going to consider functions that satisfy Rolle's theorem, and then we're going to find the points of C where the derivative is equal to 0. Okay, so if I look at the graph of x squared plus 2x on the interval from -2 to 0, this is a quadratic. So I know for a fact over all the reals, this is going to be a continuous function and it's differentiable at all points. So it's definitely going to be continuous and differentiable on one small interval from -2 to 0 if it's continuous and differentiable over the reals. So we know that it's continuous and differentiable on that interval, -2 to 0, so it works. We also have to verify that our endpoints have the same y value. If I plug in -2, I'm going to get out 0. That's my first endpoint, that's my A. Here's my value of B on my interval. If I plug in f of 0, I get 0. So my f of A is equal to my f of B, and my endpoints have the same y value. So now we have all the criteria met stated in Rolle's theorem. So I'm going to now try to find the value of C where the derivative is 0. So I'm going to take the derivative of x squared plus 2x. So that's going to be 2x plus 2. And I'm going to set that equal to 0. And I'm going to get that x is equal to -1. So that means f prime, so the derivative at -1 is 0. And you can see when we look at the graph at x equals -1, we have a tangent line that has a slope of 0. So this works. Now let's look at the next example. So we're going to do the same thing. This is a polynomial, x to the third minus 4x, so I know it's continuous and differentiable. All polynomials are continuous and differentiable over the reals, so they would of course be continuous and differentiable over a smaller interval. We want to make sure that our endpoints have the same y value, so we're going to find f of -2, and we're going to find f of 2. Those are our endpoints for A and B. And we want to show that they're the same. So if I plug in f of -2, I'm going to get out 0. And if I plug in 2, I'm also going to get 0. So these are the same, so it meets that criteria that f of A is equal to f of B. So now what we can do by Rolle's theorem, we can say there's at least one value of C on that interval where the derivative is 0. So let's take the derivative of f of x. So that's 3x squared minus 4 when I take the derivative of f. And now I'm going to solve this for 0. I'm going to put 0 in for f prime of x and solve for x. So I'm going to add 4 to both sides. I'm going to use the square root property here. I'm going to divide by 3. And so when I square root both sides, I get plus or minus 2 over the square root of 3. When I take the square root of both sides, I get plus or minus the square root of 4 over 3, but then I can simplify. The square root of 4 is 2. Now, if we want a decimal approximation, I'm going to take 2 divided by the square root of 3. And so my decimal approximation would be plus or minus 1.155 if we round it to 3 places. So if I come over to a little bit past -1, that's where my tangent line is 0. And then if I come over a little bit past 1 here, that's where my tangent line is 0. So I can say if I plug in -2 square root of 3 into the derivative, I get 0. And if I plug in positive 2 over the square root of 3 into the derivative, I get 0. So those are the two x values in which we have a tangent line with a slope of 0. Okay, now let's talk about the mean value theorem. The mean value theorem states that if f is continuous over the closed interval from a to b, and it's differentiable over the open interval a to b, then there exists at least one point on the interval so that the derivative at that point c, then the tangent line at that point c has a slope that is the same as the secant line that runs between the two endpoints. So this is the slope of the secant line that runs between the two endpoints. And then this is the slope of the tangent line at point C, and this is saying that they're going to have the same slope. So Rolle's theorem is really just a special case of the mean value theorem. In Rolle's theorem, we consider differentiable functions defined on a closed interval where the two endpoints have the same y value. But in the mean value theorem, it generalizes the Rolle's theorem by considering functions that do not necessarily have the same y coordinates of the endpoints. So basically, the mean value theorem says that if a function that meets this criteria in the mean value theorem, at some point, the tangent line is going to have the same slope as the secant line between the two ends. This is basically what it's going to say. So let's look at this example and work through this. It says verifying that the mean value theorem applies. We have the square root of x over the interval from 0 to 9. We need to show that f satisfies the hypothesis of the mean value theorem. And therefore, there exists at least one value on that interval from 0 to 9 so that the slope of the tangent line at that point C is equal to the slope of the secant line that connects those two endpoints. And then they're going to find these values of C that's guaranteed by the mean value theorem. Okay, so we know that the square root of x is continuous over the interval from 0 to 9, right? The square root of x has this kind of a shape. So from 0 to 9, we know it's continuous. There's no breaks, no holes, no jumps. There's no points or cusps that we have to worry about so that it's differentiable on the open interval from 0 to 9. And because of this, by the mean value theorem, since it's continuous and differentiable on 0 to 9, this satisfies the hypothesis that is requested by the mean value theorem. So therefore, by the mean value theorem, there has to be at least one point C on that interval so that the tangent line at point C has the same slope as the secant line between those two endpoints. So let's first find the slope of the secant line that runs between the point 0 and 9. So if we have this point 0, this point 9, here's our endpoints. We want to find the slope of this line. f of 9, which is 3, because I plugged 9 into the square root of x, that's our function. So the corresponding y value for 9 is 3. The corresponding y value for 0 is 0. So this is the change in y. Now I want to find my change in x. If I take my value of b, which is 9, and subtract my value of a, which is 0, I get 9 minus 0. That gives me my change in x. So my slope of this line is 1/3, right? 3 over 9, which is 1/3. So now what we need to do is we need to find the derivative of f and find the value of c that I would plug in to get a slope of 1/3, because the mean value theorem says somewhere on that graph between 0 and 9, there has to be a point c that has the same slope as 1/3. So I'm going to take the derivative of the square root of x. When I do that, I'm going to get 1 over 2 times the square root of x. And so now I have 1 over 2 times the square root of x has to be at some point 1/3. And I want to find out what that value of x is. So where is my derivative have a slope of 1/3? That's what this is saying right here. So when I solve this for x, I'll use cross multiplication here. So I'm going to have 2 times the square root of x is equal to 3. I'm going to divide both sides by 2 now, so I get the square root of x is equal to 3/2. Now when I square both sides, I'm going to get x is equal to 9/4. And that's going to be 2.25 if you want to put it in decimal form. So that means that here's my value of c that falls on the interval between 0 and 9 on the square root of x that has the same slope as the line that passes through the endpoints. Here's the line that passes through my endpoints on the absolute value of x, and at the point 2.25 on this graph, I'm going to have the same slope. So one application that we can use the mean value theorem for is for finding velocity at an instant when you know the average velocity. So say, for example, you have a position function that is continuous and differentiable, and you want to find the velocity, and you want to find your average velocity over that time interval. And to stay consistent, we'll say that it's a time interval from time A to time B, so it's over some interval. We can find the average velocity over that time frame in which the object is moving by finding the slope of the line that passes through those endpoints on the position function. And if we know that the position function is continuous and differentiable on that interval, then we can use the mean value theorem. We can find when the velocity is the same as the average velocity at a particular instant. So for example, if a car is driving for an hour down a road, and you find the average velocity over that time interval is 45 miles per hour, you can use the mean value theorem to find when exactly at an instant the car was driving at 45 miles per hour. So let's look at this example here, the mean value theorem and velocity. It says if a rock is dropped from a height of 100 feet, its position in t seconds after it's dropped until it hits the ground is given by the function s of t is equal to negative 16t squared plus 100. We're going to determine how long it takes before the rock hits the ground. So when the rock hits the ground, the position is going to be 0, right? Because it's 0 feet off the ground. So we're going to first solve the equation s of t is equal to 0, which would be negative 16t squared plus 100 is equal to 0. When we do that, I'll let you do that on your own. You can just use the square root property. Subtract 100, divide by negative 16, and then square root it. And you would get that the time is plus or minus 5/2 seconds. So plus or minus 2.5 seconds if you want to put it in decimal form. Now, since we're only considering positive times, because it doesn't make sense to talk about negative seconds, we're going to say that it hits the ground 2.5 seconds after it's dropped. Okay, part B says we want to find the average velocity of the rock from when the rock is released and the rock hits the ground. Since our time interval is from 0 seconds to 2.5 seconds, that's our time interval. We want to find the average velocity. So if I plug in 0 into the position function, I'm going to get 100. If I plug in 2.5 into the position function, I'm going to get 0. So I'm going to find s of 2.5, that's my corresponding y value, minus s of 0, that's going to be my change in y, over 2.5 minus 0. And when I take 2.5 minus 0, that's going to give me my change in x. So now when I calculate this, I'm going to get s of 2.5, which is 0, minus s of 0, which is 100, all over 2.5 minus 0. That's going to give me an average velocity of negative 40 feet per second. So this is my average velocity over the time interval from 0 to 2.5 seconds. The position function is a polynomial, so we know it's continuous and differentiable over the reals, which also means that it's continuous and differentiable over the interval from 0 to 2.5 seconds. So we can apply the mean value theorem here, which means somewhere on the graph between 0 and 2.5 seconds, the tangent line is going to have a slope of negative 40 feet per second squared, which means at an instant somewhere on that graph, the velocity at an instant will be negative 40 feet per second squared. So if I take the derivative of the position function, that will give me my velocity function. I'm going to get negative 32t. And so this is the slope of the tangent line at any point on the graph. So I want to find the value of t. At what time was it exactly negative 40 feet per second? So I'm going to take negative 32t, set it equal to negative 40, and I'm going to solve for t. And I'm going to get t 1.25 seconds. So that means at 1.25 seconds, the instantaneous velocity is exactly negative 40 feet per second. Now, if we look at the graph in pink here that I'm highlighting, this is the graph of negative 16t squared plus 100. That's the position function. And if I look at, in green here, I'm going to trace, here's my average velocity. That's the slope of the secant line that passes through the two endpoints. And then I found at 1.25 seconds, which is the same as 5/4, has the same slope at 1.25, which is negative 40 feet per second. Okay, the last topic we are going to talk about in this lesson is some corollaries that came about because of the mean value theorem. And there's 3 of them. The first corollary says that if f is differentiable over an interval, and if the derivative is equal to 0 for all the x's on that interval, then f of x has got to be a constant function for all those x's on that interval. So if you think about it, this makes total sense, because if I have a constant function, here's my axes, y and x, and I have some constant function. Let's say y is equal to 5. 5 is my favorite number, so let's use y is equal to 5. If I pick an interval, let's say from 1 to 7. From 1 to 7, this piece of the graph is going to have a derivative of 0 at every single point on that interval because the function is y equals 5. So at f prime 2, my derivative is going to be 0 because at that point, my tangent line has a slope of 0. If I pick another random point on that interval, like let's say 6.9, my derivative is going to be 0 at 6.9 because at that point, 6.9, I have a tangent line that has a slope of 0. So that's what this is saying here. If every point on the function on that interval has a derivative that's 0 and the function is differentiable on that interval, then the function must be a constant on that interval. Okay, the next corollary that comes from the mean value theorem says that if f and g are both differentiable functions over an interval, and the derivative of f is the same as the derivative of g for all x on that interval, then f and g have to be the same function other than maybe a vertical shift, which is just, it varies by some constant, c. So, for example, if I had some function, f of x is equal to x squared plus 3, and I had g of x is equal to x squared minus 2. Notice, other than the constant, these two functions are the same. And what's going to happen is when I take the derivative of both of these functions, the derivative is going to be the same. So I take f prime, that's going to be 2x because the derivative of x squared is 2x. But when I take the derivative of the second term, which is 3, a constant, I get 0. Now when I take the derivative of g of x, I take the derivative of x squared, which is 2x. But when I take the derivative of that second term, which is a constant, that's 0. So because they only differ by the constant that I boxed in green, their derivatives are going to be the same. And then the last corollary gives us information about where the graph's increasing and decreasing. So if f is a continuous function over the closed interval a to b, and it's differentiable over the open interval from a to b, then when the derivative is positive, so I'm looking at this part right here, when the derivative is positive for all those x values on the interval from a to b, then f is increasing on the interval a to b. And that's going to be true because if you take the derivative and the derivative is positive, that means the slope of the tangent line is positive. So it's got to be increasing. Now the same thing goes for that part too. If the derivative is negative for all the x's on that interval, then f has got to be decreasing because the slope of the tangent line at any point on that interval is negative. It's got to be decreasing. So if we look at this graph here that gives us a visual representation, if we look at the interval from a to b, if I look at any point on that interval, the tangent line is going to have a negative slope. So that's increasing. If I look at a different interval, let's look at this interval right here in red. If I pick any point on this red interval here, then, and I take the derivative is going to be positive because the tangent line at any of those points is going to be positive. And then if we look at the last interval here, same idea. No matter what point I pick on that interval, I'm going to have a tangent line that has a positive slope. So wherever the tangent line has a positive slope, the graph is increasing, which also means the derivative is positive. Wherever the graph is decreasing, that means the derivative is negative, and the slopes of the tangent line on that interval has got to be negative. And that's what this theorem is saying.